Today, we're going to talk about circuit elements. Now, you probably already know about resistors, but what you might not know is what makes them different from a light bulb or a diode or any other thing you might find in a circuit. When you're using a resistor, if you double the voltage, it doubles the current, and so on. More amperage for more voltage, always moving in lockstep. For this reason, resistors are called ohmic. That is to say, they obey Ohm's law, with the ratio of the voltage to the current being a constant slope. In this case, the slope is 15 ohms, or volts per amps. For a light bulb, this is not the case. As the voltage increases, the light bulb heats up and glows, and that changes the resistance, so you don't get as much amperage for the same amount of voltage, or twice as much. As you double the voltage, you won't get double the amperage. A light bulb is not ohmic. On the graph, the light bulb looks like this, with the slope, the resistance increasing as the voltage and temperature increase. This is a relationship that Dr. Ohm understood perfectly. This is a diode. It's an unusual circuit element in that it only lets current go in one direction. That's this direction, toward the stripe. Here I've set up an alternating current, a current that goes backwards and forwards, and the resistor handles it just perfectly. But when I hook a diode to the circuit, watch what happens. It only lets the positive current go through. For this reason, diodes are often found inside of AC-DC converters like this one. There it is. They help to turn alternating currents into direct currents, make them act more like batteries. These are LEDs, or light-emitting diodes, and you see them everywhere. The reason being is they don't have to heat up as much to glow like a regular light bulb, and so they're much more efficient. This device is called a rheostat, or a potentiometer, or a variable resistor, or a dimmer switch. It changes the amount of resistance. It controls the amount of voltage that the light bulb is getting. Another important circuit element is a fuse. A fuse is a device used to protect your circuit when you accidentally draw too much current. Here, a piece of steel wool is standing in as a fuse. Watch what happens when I accidentally short this circuit with a wire. The steel wool protected the circuit by blowing out as a fuse. We monitor our circuits with voltmeters and ammeters. An ammeter has very low resistance, and it is wired in series with the circuit you're measuring. The current goes right through the ammeter when you make a measurement. A voltmeter, on the other hand, has very high resistance, and it is wired in parallel when you make a measurement. Now, if you were to hook up these probes the wrong way, what would happen? Here is the voltmeter being added to the circuit incorrectly in series. The circuit fails. Here's the ammeter being hooked to the circuit incorrectly in parallel. The circuit fails. This device is called a transformer. It's transforming a large voltage into a small one. It only works on AC currents, and for this reason, almost all electrical power is sent by AC. You've probably seen transformers on high voltage power poles. They step the voltage down from high voltage to safer levels for in-house use. These devices are called capacitors. They're used to store up charge so it can be delivered to the circuit later on. Here I have a capacitor hooked in series with a light bulb and a 9-volt battery. When I connect the capacitor, initially you see the bulb glows very brightly. But as time goes by and the capacitor becomes charged, the light bulb begins to dim. Now that the light bulb is almost completely dimmed out, I'm going to remove the battery from the system. The light bulb goes out, of course, but when I reconnect the capacitor to the bulb, it glows brightly again. The capacitor was charged up enough to cause the light bulb to glow brightly, at least for a while. Once again, as the capacitor loses charge, the light bulb will dim and the current will go back to 0.